All right, let's dive right in. We're going to talk about something that astronomers have dreamed about for, well, forever. It's a question that pushes right up against the very edge of what's even possible.
So here's the big question. Can we actually see continents on a planet just like ours, but orbiting a totally different star? And I don't just mean finding a tiny little dot of light. No. I'm talking about actually mapping it, seeing its oceans, its land masses, all from light years away. It sounds like total sci-fi, right? But believe it or not, scientists are already working on how to do this.
So why can't we just do it with our current telescopes? Well, it comes down to a hard limit in physics. It's kind of like when you zoom in on a photo on your phone, right? Eventually, it just gets all blurry and pixelated. Telescopes have the same problem. It's called the Rayleigh limit. And to get the kind of detail we're talking about, say for a planet 40 light-years away, you need a telescope mirror that's kilometers wide. I mean, we can't build that. We definitely can't launch it into space. So just building a bigger mirror, that's not going to work.
And this is where things get really cool. The solution isn't about building a bigger mirror at all. It's about building a completely different kind of eye on the universe, an instrument that taps into the bizarre, mind-bending rules of quantum mechanics and uses matter that's been chilled to temperatures colder than you can possibly imagine. So, where do we find this new technology? Our journey actually starts in orbit, aboard the International Space Station, and we're headed to what is, literally, the coldest known place in the entire universe. It's called the Cold Atom Lab.
Okay, so what is this thing? The Cold Atom Lab, or CAL, was sent up in 2018. It's about the size of a mini fridge, and it's all controlled remotely from Earth. And it has one single job: to get atoms colder than anything else in existence. It creates these extreme conditions that, down here on Earth, we just can't maintain for more than a split second. Now, to give you an idea of just how cold we're talking, you know, the vacuum of deep space is pretty chilly, right? It's about 3 Kelvin, which is minus 270 degrees Celsius. But the Cold Atom Lab, it gets down to picokelvins. We're talking billionths of a degree above absolute zero. That is, get this, billions of times colder than empty space itself. It's just wild. But why? Why go to all the trouble of putting this freezer in space? Well, the answer is one word: gravity. Down here on Earth, the moment you get these atoms super cold and try to study them, gravity just yanks them down and your experiment is over. We're talking fractions of a second. But up there, in microgravity, the atoms just float. They hang there, and scientists can watch them do their weird quantum thing for up to 10 seconds. Now, 10 seconds might not sound like a lot, but in quantum physics, that's an eternity. Okay, so what happens when you chill matter down this much? You actually unlock a whole new state of matter. It's a state where the normally invisible rules of the quantum world suddenly become big enough for us to see. This state is called a Bose-Einstein Condensate, or a BEC for short. People often call it the fifth state of matter. The best way to think about it is like this. Imagine every single atom is its own little wave in a pond. As you get them colder and colder, they slow down, and their waves start to overlap. Until, bam! They all merge together and start acting like one single massive wave. This superatom, as they call it, basically magnifies quantum effects so we can actually study them.
Making one of these things is like a carefully choreographed dance. It's a 3-step process. First, you hit the atoms with lasers from every direction. Each little photon acts like a speed bump, slowing the atoms way down, which chills them. Then, you use magnetic fields to trap them in this sort of invisible bottle. And for the grand finale, you slowly let that magnetic trap expand. As it expands, the atoms cool down even more. It's the same reason a can of compressed air gets freezing cold when you spray it.
Okay, so we've made a superatom in space. Cool, but what does that have to do with seeing continents on a distant world? Well, this is the moment we connect that really fundamental physics back to our huge astronomical question. This is the leap. And let me just be super clear here. This is not just some sci-fi fantasy or wild theory. This is happening. We are literally watching a new field of science being born, and the proof is showing up in the most prestigious scientific journals on the planet.
Take this paper from 2020, published in Nature. This was the big one. A team from NASA's JPL proved, for the first time ever, that you could reliably make and study these Bose-Einstein condensates up in orbit. That was the crucial first step. It was the, hey, this actually works moment that everything else is built on.
But the idea itself has been around for a while. The theoretical blueprint was actually laid out back in 2012. This paper basically said, hey, you know how we're stuck with the size of our mirrors? Well, what if we used quantum networks to link telescopes together and just bypass that limit entirely? It was a plan to create a telescope with power we can barely even imagine.
Think about what this means. It's like we're being handed a whole new set of tools to explore the universe. We're talking about something called Atom Interferometry, using these atom waves to map a planet's gravity so precisely you could find an ocean hidden under miles of ice on a moon like Europa. Or imagine a fleet of satellites, spread out over millions of kilometers, all linked together by quantum mechanics to act as one single gigantic telescope. This stuff could even help us finally hunt down dark matter or push Einstein's theories to their absolute limit.
So, the big question is, how do we get from here, this little fridge-sized box on the ISS, to there, mapping a world light years away? Well, it's not going to happen tomorrow. But there is a plan, a very real roadmap for how to get to that incredible future.
Yeah, this is definitely a long game. For the rest of this decade, it's all about building prototypes and just making sure the core tech works in space. Then sometime in the 2030s, we'll probably see the first real missions, using this tech to map the gravity of the moon or maybe even Mars in incredible detail. By around 2050, we might see the first test run of a quantum-linked telescope array. And then, the big one. Sometime after 2070, the hope is to have a full-scale array up and running, ready to take that first, unbelievable picture of the surface of another Earth. And if you want to understand just how powerful this could be, here's a little fact for you. A telescope built on these quantum principles would, theoretically, be so sharp it could spot a tennis ball sitting on the surface of the moon while looking at it from Earth. That's just staggering. That's the power you get when you start using atoms themselves as your lens.
So, what's the big takeaway here? We are standing right on the edge of a revolution in how we see the universe. For centuries, it's been about bigger lenses, bigger mirrors, the age of reflection and refraction. Now we are entering the age of quantum interference. That little cold atom lab on the ISS, that's the first flight at Kitty Hawk for this technology. It's the very beginning. And it just leaves you wondering, right? When we finally build these new quantum eyes and point them at the stars, what are we going to see?